Hi guys, welcome back to Digital Electronics. Today we're going to talk about the 2's complement arithmetic. Alright, we're going to get into it just a little bit today. There's a couple ways that you can do this that we're going to cover in the PLC class, but we use the 2's complement in order to do subtraction. Okay, so for us to subtract in binary, it's a little bit more complicated than just our normal subtracting and borrowing and things like that. So we can use two different methods. We can use the 1's complement to do subtraction, or we can use the 2's complement to do subtraction. We're going to go through the 2's complement today just to talk about it. We'll do some practice problems on your assignment, things like that. Okay, so we're going to figure out how we use the 2's complement process to go about doing all this. Alright, so why do we need to? Well, that's how we handle negative numbers. Okay, so in general, when we're doing binary numbers, there's frequent addition and subtraction of numbers that has to happen. So you have to design in an adder, but there's not really anything called a subtractor because we can still use an adder, but we're going to use the 2's complement to add instead. And a 2's complement, remember, is just a different way of rewriting a number. So we can still use the adders that we learned about in the last action. I can't speak today, I apologize. We are going to use the adders that we learned in the last lecture to be able to subtract as well. But we use the 2's complement to the number. So you just have to take the 2's complement and then we add. So it's kind of like subtracting one number from another number is the same as making a number negative and adding it. It's really that basic, kind of as we go through it. So, why is this an issue for us? Well, we don't simply put a minus sign in electronics. Okay, we have to be able to handle everything in terms of ones and zeros. So we don't need to equate everything to a minus sign. Now, does it do it all? Yes, when we use your calculator and things like that. But your calculator still runs on this principle in the background. Okay, so we have to represent negative numbers a specified way when we're using a binary system. Okay, we set the length of the number, okay, how many strands it is, and then we set generally anything that starts with a 0 is positive, and anything that starts with a 1 is a negative number. Okay, we'll take a look at that in a little bit. But when we do all the arithmetic, it has to be a fixed length number system. Alright, so we have to make sure that we assign all the numbers correctly so that whatever's on top has the same number of digits as whatever's on the bottom. It has to, because we have to have fixed length because we're talking about binary numbers. So we have to be able to store that memory, and we have to have a specific number of bits to hold that place. It's kind of like holding your place when you did original arithmetic and things like that. So we have to make sure that everything lines up. So we can, obviously add a number of zeros in front. Now, what does that mean, though? What I want you to really be careful of when we get into binary numbers and making them negative and positive is the number is only negative when it applies to us adding. Okay, so I really want you to think about that. So, the number like 1111 represents 15 if we're counting, but if we're doing subtraction, alright, it's a negative number. So we really have to pay attention and understand, are we doing the subtraction, okay, or are we actually using the binary number as the number 15 or something else like that. So it's really important when we go through this. Okay, same kind of concept here. Don't let this confuse you in any way. Alright, so this is if we did it with a 3-digit decimal numbering system. Okay, so what did we really do? We kind of work backwards. We do the same thing, only we can use signed numbers in the decimal system. And this way seems to kind of confuse you a little bit, but so if we have a bike odometer, okay, that has 3 digits, that's a fixed length decimal number, right? So it can go from 000 up to 999. Okay, anything counting up is going forward. Anything going the other direction is going backwards, or considered negative. Okay, so we can do the whole problem without a negative sign. All right, you cannot tell the difference between a positive 998 from a negative 2. All right, so I guess the question is, right, did you ride forward for 998 miles or did you ride backwards, for 2 miles? We can't, specify there. So, that's why we represent things differently. So, if we represent negative numbers in this same type of system, there's not going to be a lot of work on the negative decimal here. I understand that this is confusing, okay? But if we cut the number system in half, okay, and we only use 001 to 499 to indicate positive numbers, okay, then we want to use 500 to 999 to indicate negative numbers. So that's what we're really going to do, okay, so that we can span and go from, negative 500 up to positive 499. And there's how we would count, okay? So negative 500 would be represented by the number 500, okay? And negative 1 would be represented by the number 999. So see how we're taking that and incrementing the other way, because they have to offset, right? Y is negative 001, right? That we have to represent it with 3 digits. So that's why negative 1 is represented as 999, where negative 500, all right, is represented as 500. So we notice that the combination, gives us what we're missing there to get to that 0, please. Okay, so we have to also remember that the 000, it's not positive or negative, right? It's neutral, it's lying in the middle there. Don't fret on this if you're not getting this. It's going to make a lot more sense when we do regular binary numbers. Okay, so for us, for you and I, and how we grew up, right, we can do simple math. 3 plus 2 is 5. 6 plus a negative 3 is 3. That's the part we're going to focus on when we get into doing the 2's complement. If we have negative 5 plus 2, we want to be adding when we're doing this. So we're just going to change the numbers so that when we add them, they work out right. And then we determine at the end if it's a positive or a negative number based on the digit that's in front of our binary number. Okay, so if we take a look at these and we're using what we talked about on the previous slide, right? We're using a 3-digit decimal number. We have 003, 002, and when we add those, we get 005. Okay, if we go the other way, we have to use 006, and then instead of negative 3, we use 997. We're looking at the other page over there, and now we add. Okay, so what do we add? We get 1003, right? But we're going to disregard that, and that number actually is our positive 3. So the 1 in front, it just tells us we're going to disregard it in this way because the way we have the decimal system set up. All right, so let's look at the next one. We know that negative 5 is the same as 995, and we're using 2. Now remember when I first started talking about this, that we have to have the same number of digits. So this is a 3-digit decimal. All right, so that's why there's zeros in front of the 2 here, zeros in front of the 5, and that sort of thing. Because the negative number is larger than the single-digit ones. Because remember, we deemed that anything from 500 to 999 is a negative number. So we can use the opposites of those. So that's why once we get to 1,000, we discard that 1, and it makes the number positive again. Okay? Or if we end up with a number that's between 500 and 999, we know that that ends up being a negative number. Okay, so it translates back. So that's the really cool thing about using this type of system with binary. So if we rewrite negative 2 as 998 and negative 3 as 997, okay, we can combine those and we get 1995, but we disregard the overflow and we get 995. Okay, 995 is the same as negative 5. Once again, because the decimal system here we used, and I'm going to step back a couple slides, we're using this. Okay, so that's why I know it seems a little confusing, but we're using the 3 digits. So remember, any number from 500 to 999 is a negative number. Any number from 001 to 499 is a positive number. So that's how we're going to translate and get our results here. Okay. okay? It will work out when we do binary, okay? So this is how the process works, okay? That's not how it works in electronics. We have to be able to do that with binary. But that's kind of to help you kind of simplify and see where we're going with this. So we only used numbers, what? 1 through 999, right? 0 is neutral, and anything over 1,000 we discarded. So if we got a number that was between 1 and 499, it was a positive number, and it was that number. And then if we got a number between 500 and 999, it was a negative number, all right, and that translated back to whatever the negative value was, okay? It's not as easy for large numbers to do this process, all right? So it can get a little confusing. So we can use the tens complement process, okay? So nobody really uses this. I just want you to know that. It's more for your indication and understanding. We're going to get into the meat and potatoes here, what we're doing here, all right? So remember, tens complement, we're going to use a base 10 because we're talking decimals. We're going to get into the twos complement a little bit using binary, okay? And what we're doing is when we do the tens complement, all right, we're going to complement all the digits of a specific. So first, when we complement the number, okay, a digit's complement is the number you add to the digit to make it equal to the largest digit in the base. Okay, so 9 for decimal. The complement of 0 is what? 9. Okay, because that's the most digits we can get. The complement of what? 1 is 8, because 1 plus 8 is 9, right? The most digits we can get for decimal is 0 to 9, okay? That's 10 digits. So 2's complement is 7, right? Because 2 plus 7 equals 9. Does that make sense? 3's complement would be 6, because 3 plus 6 is equal to 9. 4's complement is 5, because 4 plus 5 is 9. So that's the first thing that you have to do when we do the tens complement. You take its complement, so 1's complement is 8, and then we would add 1 to that number. So to find like the complement of 1, or the tens complement of 1, okay, we would first complement it, which is 8, and then 8 plus 1 is 9, okay? Let's do it differently because I know that the 1 kind of throws you off. So let's say we're going to take the complement of 3. The complement of 3 is 6. The tens complement of 3 would be 6 plus 1, which is 7, okay? So if we have to do that adding the 1 because we'd have too many zeros. We cannot have a plus 0 and a minus 0. We have to make sure that 0 stays neutral when we do this, okay? All right, so let's take a look here, and let's take the tens complement of negative 0. So what's our first approach? We got to find the complement of 3. We're still using that table from before, right? So its complement is 996, okay? Because we have to use what we did before. Notice an easier way to figure in your head here is if you break down each digit. Okay, the 3's complement, the complement of 3, sorry, let me rephrase that so it makes more sense. The complement of 3 here is 6, right? Because 3 plus 6 equals 9. The complement of 0 is 9, because 0 plus 9 is 9. And that happens twice in this case. Okay, so there's really how you can find the complement. Okay, so that's the 996, and then we have to add 1 to that. So we just found the tens complement of this number is 997. Okay, so let's look at negative 214. Maybe pause the video real quick and see if you can do this one on your own. Alright, so you're going to take the complement of 4. I'm sorry, I'm going to rephrase that. I keep saying the complement, the tens complement. It is important what we're doing there. Alright, so you got to take the tens complement of the 4, the tens complement of the 1, and the tens complement of the 2. Okay, so pause it, give it a shot, and then resume, and we'll be here working with you. So we know that the tens complement of 4 is 5, because 4 plus 5 is 9. We know the tens complement of 1 is 8, because 1 plus 8 is 9. And we know the tens complement of 2 is 7, because 7 plus 2 is 9. Okay, so this number gives us 785. Last step, we have to add 1 to this, so our final answer for the tens complement is 786. Okay, so the tens complement of negative 214 is 786. Notice if you remove the negative sign, so if it's not negative 214, you can see that 214 plus 786 equals 1,000. You're really just finding the difference between 1,000 here in the tens complement. If we look at example 1, if we take that negative off there, we know that 997 plus 3 is equal to 1,000. So you're really it's almost, a simplistic way would be two numbers that add up to 1,000. So, or I can just take that number and subtract it from 1,000. Okay, so if I take 1,000 minus 003, I'm left with 997. If I take 1,000 minus 214, I'm left with 786. Okay, so there's a couple different ways that you can think about that. Not necessarily as easy when we get into binaries. Okay, if we start doing this with 8-bit binary numbers, okay, we have to start allocating. And remember, as we allocate this, it only applies to when we are adding, subtracting binary numbers. If we are using counting numbers, we are not going to say that a 1 is a negative and a 0 is a positive. Okay, so just make sure that you understand that. So, but the same approach always occurs here. Okay, so we have to take our numbering system, all right, and cut it in half. So just like before, we had 1,000, right? We cut it in half. So we went from 0 to 499 and went 500 to 999. Do the same thing in binary here. Okay, so we're going to take, we want to go from, 0, 0, 0, 0, 0, 0, 1 to 0, 1, 1, 1, 1, 1, 1, 1, right? So that's going to be our positive chunk, because essentially what? If we have to do the entire system, so let me back up. We are going from 0, 0, 0, 0, 0, 0, 0, 0. I said 0 8 times if you're counting, okay? And then we're going up to 1, 1, 1, 1, 1, 1, 1, 1. I said 1 8 times, okay? That's what we're counting for our number system here, okay? When we cut that in half, okay, you can see on the screen here what breaks down to our positive numbers and what breaks down to our negative numbers. Notice, very important when we're doing this, any of the binary numbers that have a most significant bit or the leftmost bit is a 0 is a positive number. If the leftmost bit is a 1, we get a negative number. So that's really, how we're adding and subtracting using binary numbers. But you have to limit the system. So this is limited to 8 bits. Alright, so everything, all of our numbers have to align properly for memory and for signing. Okay? So I already kind of said this on the last slide, right? The MSB, the most significant bit, if it's a 0, the number's positive. If the MSB is a 1, the number is negative. Okay? So hopefully you're starting to kind of get the gist of here. Now, we're going through all this and we're going to do some subtraction. It's not as difficult as what we're doing here. Okay, so let's learn how to find the 2's complement. And we only apply the 2's complement because we're talking about binary numbers. We used the 10's complement because we were talking about decimal numbers. Okay, so make sure that we really understand, kind of what's going on there. Okay, so there's 2 steps to finding the 2's complement of a number, and we're going to use the 2's complement. It's going to be very important for us to be able to do subtraction because we're actually going to use addition to do subtraction. Okay, so the first thing that you have to do when you do the 2's complement of a number, you have to take that binary number and you have to make all the 1's 0's and all the 0's 1's. So you're going to swap everything. If it was a 0, it became a 1. If it was a 1, it becomes a 0. That's the first step. So that's called the 1's complement. So we're going to take the 1's complement of the binary number first by changing all the 1's to 0's and all the 0's to 1's. So make sure that you write that down and understand that. The second step, so this is what distinguishes between using the 2's complement and the 1's complement, is that you have to add 1 to the 1's complement. Okay, so after you've changed all the 1's to 0's and 0's to 1's, you have to add 1. Just like we did with decimals, we have to add that 1 so that we don't have a negative and a positive 0, which don't exist. Okay, so let's take a couple examples here. Okay, so we're going to take the 2's complement here. Okay, so what's the first step? We've got to change all the 0's to 1's and all the 1's. So we can go ahead and rewrite that. Okay, so that's what we're doing. This is the 1's complement right here. We just found the 1's complement. We changed all the 0's to 1's and all the 1's to 0's. Very important. Now next step, to get the 2's complement, we have to add 1 to this 1's complement that we just found. Okay, so we're going to add 1 here. And when we add 1, right, just doing our basic arithmetic and binary, right, 0 plus 1 is 1. We get the number 1, 1, 1, 1, 1, 0, 1, 1. Okay, that equates to the negative 5. Notice that's how we took 5 and we wrote the opposite of 5. That's what we're doing, because we can use the opposite of 5 to do addition with negative numbers. So we know that 5 is represented by what? 1, 0, 1. Okay, and the negative 5 is this large number here. Okay, all right, why don't you pause the video and try and do the 2's complement of negative 13 here on your own, and then we'll be working through it. Okay, so when you hit play, we'll be working through it. All right, so first step here, you got to take the 1's complements. We got to take all the 1's, change them to 0's. Okay, so we get that number. I don't need to read off all the 1's and 0's for you. And then the second step, we have to add 1 to that number. Okay, and notice that's how we get positive 13. So very, very, very important how we get these numbers. Okay, they don't align to our counting numbers. Okay, so it's very important that what we're working on and doing this only applies to adding and subtracting binary numbers. It does not apply to like storing the memory piece for something different. It does not apply to when we are counting from 0 to 15. You have to distinguish between that we are using the 2's complement to add and subtract. So, you know, in real life, that number 1, 1, 1, 1, 0, 0, 1, 1, it can have multiple meanings. We can use it as negative 13, or it can be an 8-bit code for something, and that 1 means something. It doesn't necessarily mean the number's negative. So I just want you to kind of be aware of that. All right, so let's do some examples here of, you know, common stuff that we know. 9 plus 5 is 14, right? We know that negative 9 plus 5 is negative 4. Okay, this is all, you know, basics for us. We can see that we're going to add the opposite. So instead of saying add, you know, a negative, I want you to start thinking about we're going to add the opposite so that we can get in the right spot and come up with the, you know, correctly signed number. Okay, now when we do numbers, all right, so 9 plus 5, we know it's 14, right, in decimal. Here's what you need to know. If we don't have any negative numbers or we are not subtracting, you do not need to use the 2's complement. Add numbers like they normally are added. Just rewrite them, all right? You know, it's general form to keep it in, you know, 8-bit and that sort of thing, or 9-bit, or whatever forms that you want to hold out here, okay? So, in this scenario, we would just add these two numbers together just like normal. Okay, it's very, very important that you do this. Okay, don't do the 2's complement if we're just adding. So when we add these up, we get 14, straight up adding. Remember, 1 plus 1 is 0, and we carry, we've gone over how to add in binary before, but 1 plus 1 is really 2, right? 2 is written as 1, 0 in binary. So we keep the 0 down and we carry the 1 at the top. So if you need to revisit adding and subtracting, go ahead and do that, but that's where the carry bit comes in. Okay, now we see that we're going to take 9 plus a negative 5 here. So now we have to use the 2's complement to impact that negative number so that we can add and actually get 4. Okay? Now, what do you take the 2's complement of? You only take the 2's complement of the number you're subtracting. Okay? Do not take the 2's complement of 9. You only take 2's complement of the negative number, which is negative 5. Okay, so very, very important here. So 9 still stays the same. Okay, 5 we have to take the 2's complement of. So we write 5 out first. Okay, we write 5 out first. So that's what 0, 0, 0, 0, 0, 1, 0, 1 is. That's 5. Then we have to take the 1's complement, so we change all the 0's to 1's and all the 1's to 0's, and then we add 1. Okay, so we take 5 and we take the 2's complement of it so that we actually get the negative number. Now we take that number at the bottom and add it to the 9. Okay, so that's going to get replaced right there. Alright, and then we do our normal binary addition. Okay, so 1 plus 1 is 0 with a carry 1. 1 plus 1 is 0 with a carry 1. Now, notice when we have all the bits lined up, if there's a carry at the end, we ignore it. See that one that has a line through it? That was an end carry. If you actually did the math here, alright, there's a whole bunch of 1 plus 1, which is 0, and the carry bit keeps going. If you end up with a carry bit, right, and there's, remember, look how many bits we started with, right? There's 1, 2, 3, 4, 5, 6, 7, 8, right? We have 8 bits that we're looking at. So, we don't, if we put 8 bits in, we don't want 9 bits out. Okay, everything's got to stay strategically aligned. So, since that 1, when it carries down, creates a 9th bit, we disregard the 9th bit. Okay, so our number is actually the 0, 0, 0, 0, 0, 1, 0, 0, which is the same as 4. Okay, and since there's a 0 in front, we know the number is positive. If there isn't a carry, okay, you have to add 1 to the number at the end. Okay, so let's take a look and see what happens there. Okay, so let's look at this example. This is now negative 9 plus 5. Okay, 9's the negative number, so we have to take the 2's complement of the negative number. Okay, very, very important here. This is the 2's complement of the negative number. So when we do this, we found the 2's complement. I'm not going to go through that again. You should know how to do that. We rewrite the 2's complement there. We do not take the 2's complement of 5 because 5 is positive. Okay, so 5 stays the same. We do our binary addition. Okay, and now look. There's no carry bit here. Since there's no carry bit, this answer is negative. Okay, it's negative. Now for us to find out what the negative number is, okay, so there's 2 ways to do this. One is we leave it as this number here, and we know that it's 1, 1, 1, 1, 1, 1, 0, 0. That might not be nice for us to know that it's negative. Okay, we may not understand that that's negative as easy. Okay, so it's tough. You have your table and you got to look at, but since there's a 1 in front here, we know that that number is negative. Okay, hopefully that makes sense. Okay, so we have to check to see if it's correct. Okay, so we want to see that. How do we check that? Now, and like I was saying before, we see that the 1 in front tells us it's negative, and we have the number 1, 1, 1, 1, 1, 1, 0, 0, right? That's not a nice number for us. How do we know that that's negative 4? So we can take, the 2's complement of that number to see what it is. So this is just checking to see, right? So we took the number that we added and found, and we took the 2's complement of it, right? We switched all the 1's to 0's, all the 0's to 1's, and added 1 at the end. 0, 1, 0, 0 is 4. So we knew that that's 4. Okay? So what you can do is you can either leave this number as 1, 1, 11110, and know that the answer is negative because the first bit, the most significant bit, is a 1. Okay, or you can retake the 2's complement at the end and put a negative in front of it. So I could write that answer down below as negative 0.00000100. Same kind of concept there. So you'll get the gist of this. Just you might have to watch the video a couple times, go through what's going on here to really get a good sense of it. But that's a good thing about having a recorded lecture, so you can pause this and listen to it multiple times and hopefully eventually sinks in. Alright, so let's do one more example here, okay? Because you're like, well, Mr. Slutty, what if they're both negative? Do I need to take the 2's complement of both? And yes, you do. We already did this, so I'm not showing the steps here. We did this in the previous 2 slides. We've already taken the 2's complement of -5, or of 5, and the 2's complement of 9. We've already done those. They're on the previous slides. So yes, you do take the 2's complement. Every single negative number you have, you will always take the 2's complement of it and then do the addition. So in this case, we end up doing the addition, and there's a carry bit at the end. We always ignore the carry bit when we are using the 2's complement method. Always ignore the carry bit when we are using the 2's complement method. Okay? You saw if we didn't have a carry in the previous slide, that it meant the number was negative, and then we could have rewritten that to verify, so we knew exactly what the number was. Okay. And then if we want to know, because 1111010, okay, that's tough for us to tell that that's 14 or -14. Okay, so we have to take that number and do the 2's complement of it to tell us that it's equal to 14. Okay, so if we take the number we got, we take the 2's complement of it, and it tells us, yes, indeed, all right, that's 14. So we can distinguish now, leaving it in the 1111010 form is the equivalent of -14. In that first bit, the MSB tells us the number's negative. And then we verified with the 2's complement to understand what the actual number is. That is negative. So when we took the 2's complement of it, we could see that it is indeed 14. It's easier for us to see that 1110 is 14, right? Because we know that 1111 is 15. So very easy for us to kind of see that that's -14 there. Alright guys, we'll do some more examples on the board so that we're a little bit more clear about how we use the 2's complement. But, this is how we work with binary numbers that are negative. There's a 1's complement method, but I don't want to confuse you, alright? Let's stick with the 2's complement method. Just a couple simple rules, right? You should know how to take the 2's complement. And then when do we take the 2's complement? Anytime we have a negative number and we need to add them. So every time you see a negative number show up, you're going to take the 2's complement. Okay, so once we go from there, alright, you're going to add them. And you need to remember, if the most significant bit is a 1, alright, the number's negative. If the most significant bit is a 0, it's positive. And the last step you need to understand, if there's a carry bit that comes down after doing all of your binary addition, you ignore the carry bit and you stick with the given number. Okay? So we'll review it again in class, but you might have to watch this a couple times to understand it, and that's okay. And that's a good thing about having these recorded. But like usual, guys, email me with any questions or let me know if you got a Zoom meet or team meet or anything